Good morning. How are you doing?
I'm good. How are you, Ava?
Good.
I
Good morning, everyone. We'll be starting shortly. We'll wait for Professor Bojatek to come in and then we'll start, if that's okay with you.
Yes. So you mentioned that this is basically recorded, right?
Yes. And then with your permission, we'll post it. But if you would not like us to post it, we can go ahead and delete it. I just sent her an email, so we'll give her a few more minutes and then we'll just go ahead and start.
Hello. Hi.
Hello.
Good morning.
Hi. Sorry for my late. I think I was on an accidental and a different Zoom link on the calendar. I think there was two ones. So sorry for that.
That's okay. Thank you for joining. We're happy to have you now.
Hi. Hello, Professor Kaoumi.
Hi.
Is it Kaoumi?
Kaoumi, Djamel.
Djamel Kaoumi. Nice to meet you. And should I start? Yes. Hi, everyone. I wish I can put my camera on. Unfortunately, I have a laptop from my laboratories and it's a bit difficult for me to put on a camera. But my name is Sandra Bogatic and I'm a professor at UT, and I'm very happy to introduce this webinar talked by Djamel Kaoumi from the Department of Nuclear Engineering at NC State. The talk is on studies of microstructure evolution under irradiations, highlights of nuclear material research related to radiation damage characterization in the materials under reactor extremes. I guess MATUR is their acronyms. That's a group at NCSU. I guess I will give the time for Professor Kaoumi to introduce himself and to start the presentation. I will try to moderate when to start for questions and answers at the end. I'm very pleased to be here to listen, and I will let to you, Djamel, to take over from here.
Thank you, Sandra, and please interrupt me at the end if I go too long. My understanding of this webinar series is that there is a special focus on newcomers for this consortium, to give them an opportunity to talk about their research and to give a little bit of background to the rest of the consortium, which I think this consortium has been around for more than 10 years. So the newcomers like me need to introduce themselves. And I appreciate the opportunity. I also apologize for the fact that it had to be postponed. There was miscommunication. It was supposed to happen earlier. But the bottom line is I'm here and I'm going to talk a little about some of the research done in my group and how it can be relevant also to the consortium. But I do several aspects of materials degradation under irradiation, and I obviously cannot talk about everything, so I chose to focus on a specific aspect of radiation damage characterization. So first, this is the outline of my presentation, a little bit of a few words about my group, then a few words about the motivations for studying microstructure characterization under harsh environment, especially irradiation, and then an example with the use of in situ TEM for radiation damage studies. And I'll try also to show how we are using this technique for the consortium. So this is a picture of my group, more or less up to date, with graduate students in the middle and a few recently graduated students on the right side. I also have a postdoc here, Ertugrul, who joined a few months ago. And I also mentioned, put here Professor Tim Horn from Mechanical Engineering, as not a member, but more as a co-PI, because we do have a few projects together, especially on the processing of materials for harsh environment using additive manufacturing. He's the director of the Kamal facility, the additive manufacturing facility of NC State, and is in fact a co-PI on the consortium. We do co-chair the students involved with additive manufacturing. About my research, there's two axes. One is on alloy development, especially for structural and cladding applications for harsh, extreme environment. And lately, with a focus on processing for additive manufacturing, thanks to the collaboration with Professor Horn. The other main aspect that has driven my scientific interest throughout the past decade has been investigation of microstructure property relationship under harsh environment, such as the one that is in a nuclear reactor environment, which encompasses irradiation effects, corrosion behavior, and mechanical stress. Because, as you know, irradiation, corrosion, medium, mechanical stress, and high temperature are all parameters that define a nuclear reactor. So the goal is usually the goal is to develop a mechanistic understanding of the microstructure evolution under such external solicitation, and to see how it can impact the macroscopic properties. Could be mechanical properties, corrosion properties, etc., which govern the material's performance. My investigation techniques involve both in situ and ex situ characterization techniques, with a focus on in situ techniques whenever I can. Those in situ techniques allow really to capture the process of the microstructure evolution as it occurs in the material. And for that matter, I developed an expertise in situ experiments in a transmission electron microscope, which include both in situ ion irradiation coupled with heating and cooling experiments, and in situ straining or mechanical testing in the transmission electron microscope, which means that we're looking at dislocation dynamics in crystal structures, and as well as getting some stress strain or displacement load curves for in situ micropillar testing in the TEM. The beauty of such techniques is that it allows you to observe the processes as they happen in under the solicitation, whether it's irradiation, mechanical stress, or temperature. Another technique that I have used very fondly, I would say, is in situ synchrotron X-ray tomography and diffraction for a couple of projects that I was part of in the past, such as stress corrosion cracking studies of canister steels for canisters 304 and 316. Or more particularly in situ synchrotron X-ray diffraction techniques to get information on dislocation densities as a function of strain through Williamson Hall dislocation analysis. That was especially of interest for understanding the mechanical behavior of developmental alloys of interest for DOE. In situ experiments usually involve very small samples, and therefore it's always good, if not necessary, to couple these type of experiments with bulk experiments, whether it's bulk irradiation or bulk mechanical testing, followed by ex situ characterization. That way we can alleviate, or I would say not alleviate, substantiate the effects of having a small sample, the effect of thin foil surfaces, etc. And in terms of characterization techniques, I use a lot of electron microscopy and, as I mentioned, synchrotron XRD and tomography. But the materials of interest in our group have revolved around high temperature alloys, essentially metallic systems with nickel-based alloys such as Heinz 230, Cornell 617, Cornell X750, steels, the 300 series, development steels such as the 709 steel, and developmental ferritic martensitic steels. There's a very particular interest in nanostructured alloys, such as oxide dispersion strengthened steels and nickel-based alloys, as well as more lately, multi-principal element alloys, known as high entropy alloys. So all for applications dealing with extreme environment. Few words about the motivations on specifically studying microstructure characterization under irradiation. So, as you know, this is a schematic of PWR, as you can recognize it. As you know, all of the materials that are used to build the reactor, and especially to build the reactor pressure vessel, as well as the core materials, they're all under the impact of irradiation, mechanical stress, high temperature, and corrosive medium. Even when we talk about the secondary loop, we are dealing where we don't deal with irradiation directly. We still have high temperature, corrosive medium, and mechanical stress. So needless to say that most of the metals that we use and most of the materials that we use in general are subject to a harsh environment. Their microstructure is what governs their properties. By microstructure, we talk about average grain size distribution, alloying elements, second phase precipitates, etc. And those are the features that are going to govern the mechanical properties, strength, ductility, the chemical properties, corrosion resistance, etc. When we put the material in the reactor and it's subject to irradiation and temperature, a lot of things happen to the microstructure. The atoms are displaced, vacancies and interstitials are produced, they can cluster, grow into loops, grow into dislocation networks, phase transformations can happen, precipitation or dissolution of second phases can happen. And when it's coupled to a corrosive medium, you can have an oxide buildup or metal loss, depending on whether you are in a passivating system or a non-passivating system, such as in molten salt reactors. So as a result, the microstructure changes And therefore, as a result, the material properties are going to change. So understanding how the microstructure evolution happens under irradiation, temperature, and or corrosion is extremely important to predict the material's performance and to design for better materials, whether it's for Gen 4 reactor or for any kind of extreme environment. So for that matter, I'm going to now go over the specific technique that allows us to study microstructure evolution under irradiation, and that's through the use of ion irradiation coupled with transmission electron microscopy. One of the difficulties, not the main difficulty, of studying the microstructure evolution under external solicitation, whether it's going to be irradiation, stress, or temperature, it's the lack of kinetics information, because the samples are usually examined ex situ, especially if it's a material that was subject to spend time in a reactor. We always need to wait until it's out, cool down, safe to manage, and then we can look much later at what the microstructure was. So the same thing, in fact, with the ion irradiation. If it's not coupled with an in situ investigation technique, you irradiate your sample at a given temperature, but then you have to cool it down and process your lift out in order to probe the microstructure. So given the dynamic nature of the irradiation effects, direct in situ observation is in fact useful, if not necessary, if we want to really get to the mechanisms and driving forces that are involved in those processes. And this is where transmission electron microscopy can help, because the spatial resolution of the TEM makes it ideal to continuously track the response of the system at the mesoscale. And for me, mesoscale, I say for me, because I understand that for other people, it might be a different scale. For the microscopists, the mesoscale is going to be anything in the nanometer to the micron level. And we can try to relate that to the macroscopic properties. So those in situ experiments cannot be done everywhere. In fact, for a long time in the USA, the only facility where we could do that was at Argonne National Laboratory, the facility that I'm showing here, the IVEM. Since more than a decade ago, another facility was constructed in the Sandia National Lab, with also this capability of in situ or quasi-in situ irradiation, and also multiple, I should not say multiple, that's exaggerating. Several other facilities have been developed in the world, such as in England, in France, and in China. And there are also several of them now in Japan. So showing also the interest of the community in such a technique, because it really yields information that can be pretty useful for different matters. And I'll try to illustrate that in a second. So a few words about the instrument. It's basically an electron microscope, a transmission electron microscope that is coupled with an ion beam accelerator, and we can choose the ion type, the ion flux, so we have control on the dose rate, the temperature, we can cool down, heat, and the beauty of that, of the technique, is that we can observe the microstructure using the electron beam as it is being damaged by the ion beam during the process. And that way we can get some kinetics information, but also we can get a picture and observe the spatial distribution of defects created and how they interact with the surrounding features. A few words about this stage here that I put on at the bottom. The same type of experiments can be done with a stage that allows you to strain the sample, and therefore there you can have a look at the dislocation dynamics in the metal. You can irradiate the sample and look at how the clusters and loops forming under irradiation interacts with the dislocation dynamics, etc. So there's a very interesting experiments that can be done to study the plasticity of irradiated materials. For sake of time, I will not present any of that in this presentation, but I do have some good experiments on nickel-based alloys. Radiation. So to give you an idea of where those experiments sit in the realm of radiation damage, which is a multi-scale complex phenomenon, as you know, I use this schematics that a lot of you probably have already seen in the past. It's borrowed from Brian Worth. And it basically shows you how radiation damage is a multi-scale phenomenon with processes that happen at the atomic level and at the picosecond or even less, but that can have effect at the macroscopic level, millimeter to meter range, many months or years later after accumulation of damage. And depending on which aspect of that radiation damage and radiation effects you are looking at, you're going to have to use a specific modeling approach and a specific experimental approach to benchmark the model. And for that matter, this is where we sit in terms of in situ TEM and TEM analysis of radiation damage. It's basically in the mesoscale, as I mentioned earlier, and it's to benchmark models that are based on rate theory. So what do we see? I'm showing you a little video here that we recorded for a model martensitic alloy. The beauty of the technique is that we can record videos as we wish, and we see here in this dark field some white features, white dots that are basically clusters of point defects and loops. There could be interstitials or vacancies if you can't tell by just looking at the contrast. But the bottom line is that these videos show how dynamic the process of radiation damage is. You create point defects. Those defects are formed, they sometimes disappear, they move, and they move in specific ways. And those observations are possible thanks to these videos. We can see that the defects are not necessarily diffusing in a continuous way. They seem to hop. They hop in specific directions, specific crystallographic direction, and they can go back into the previous position or move forward, etc. So first, there's observation on the dynamic aspect of radiation damage formation and evolution. But we can also do systematic experiments that will allow us to determine kinetics information, which I was mentioning earlier. I'm talking about defect density versus dose. I'm talking about loop size distribution versus dose. I'm talking about temperature effect when we do those systematically the same experiment at different temperatures. And importantly, we can also see spatial correlation of defects with the pre-existing microstructure. And that is something that I'm going to illustrate. As an example, I show you here some past study on pure kinetics information collection in model alloys, ferritic martensitic steel, that were meant to feed rate theory models. And this is this gives you an idea of what we could do. You follow the exact same region. And as you can see, you have an increase of little white dots and their size can increase. And the beauty is that we can measure the size distribution as a function of those and see how the shape of it evolves and how also the average grains, the average size of the defect evolve as a function of dose and temperature and their number density. All this information is relevant to benchmark models that are based on rate theory. For that specific study, we were working with Brian Worth and his postdoc Aaron Connard, who's now at Los Alamos, and they developed this spatially dependent cluster dynamics to represent what the in situ TEM experiments were showing. And as an example of how in situ TEM can help the modeler, I want to specifically emphasize this ultimate result, where we were giving them the kinetics information we had. And for quite some time, we had a mismatch. The trend of the model was matching the trend of the kinetics of the growth and formation of the defects, but we were off by an order of magnitude or more. And it was for quite some time, we didn't really understand why, until we looked again at all the videos, and we realized that basically the model was considering a diffusion approach that was not appropriate. And because of the way that I showed earlier in the video, the jerky motion, the hopping of the defects, the diffusion, the model should take into account that aspect. And that's basically what was done. And Aaron and Brian came up with this trap-mediated diffusion process. They actually introduced it into the model to take into account the discrete hops that we saw during the in situ experiment. And the idea is basically that your defect is trapped at a given position because of impurity or because of a defect around. And occasionally, if let's say a point cascade defect, a point defect cascade happened nearby, you can have a shock wave that is produced and will allow that this loop to free itself from the trapping side. And then at that point, it's going to glide extremely fast in the gliding direction determined by your crystal structure. And this is why we see this type of 1D motion until it's trapped in another position. By introducing this trap-mediated diffusion concept into the model, we managed to get much better agreement between experiments, and you see the curves on the right. The experiments are the clear dots, and the modeling results. Other interesting aspect that we can see is with the in situ irradiations, to learn how on mechanisms of loop and defect growth, for instance, and the effect of the material composition. So for that matter, I'm going to show you on the left an experiment that was done by Jenkins' group at Oxford in the exact same facility that I'm talking about and that I have used myself. And they were working on ultra high purity iron. And what you see here is also this dynamic picture of the radiation damage, but I would like to draw your attention to those loops that are growing, and some of them are even able to move so that they can coalesce. And you see those large finger like features in the end. This coalescence of loop will account for the kinetics observed in this in ultra high purity iron. The question is, does it happen also when we are dealing with a binary alloy or with an actual commercial alloy? And when we, for that matter, we had done very similar experiments, but using iron, to which 12% of chromium were added and a little bit of carbon to make it a steel. And doing the similar experiments, we observed very different results. The motion, the mobility of the loops is extremely reduced. In fact, they're not moving much at all. And what we observe by following on the right side is here, by following the loops throughout the experiment, is that they are able to grow, but not through the same mechanism, and certainly not through coalescence of loops, because the impact of adding chromium is reducing the mobility of those loops very much. In fact, the growth mechanism is more likely to happen by a direct absorption of point defects or very little clusters that are directly formed in the vicinity of the loops. So we can also look at the dynamic, the kinetics and the growth of the loops. Another aspect that I mentioned is the ability to look at how the spatial distribution of the defects and how they interact with the microstructure features that are already there in your material. And for that matter, I could show you on the left side the effect of grain boundaries. And if there are students looking at this video, you know that in class we always mention sinks for point defects, and for instance, that grain boundaries are sinks for point defects. They're strong sinks for point defects. But what does it mean? It essentially means that whatever will form nearby can be absorbed by it, and therefore it's removed from the matrix. And oftentimes students have a hard time picturing that, and this is why I think such experiments can be very informative. When you look at this martensite structure, you have laths, and what we can see is that through irradiation, you have an accumulation of defects. The defects grow larger and more numerous. But if you look very close to the grain boundaries, you have what we call a denuded zone. The evidence that around the grain boundary, the material seems deprived or denuded of defects. It's not because they're not forming there, it's because the grain boundary is effectively absorbing them. This is one of the driving, this is one of the concepts that is driving the community, the nuclear materials community, to use smaller size alloys, sub-micron alloys, in fact, as structural alloys and cladding material in the next generation of nuclear reactors. Another thing also that we teach in class is the concept of irradiation enhanced or irradiation induced creep. And we know that creep happens outside of irradiation, but when you add irradiation to it, you can accelerate it and sometimes induce it at temperatures that are too low to have normal thermal creep. And this is here an illustration of how radiation can help that. You can see in the beginning on those pictures the straight lines typical of the dislocation lines that you have in this martensite structure, very straight. Very quickly, after less than a dPa, in fact, you start seeing how these straight dislocation lines are affected, and they start having this zigzag shape. It doesn't matter the material, 9 chrom, 12 chrom, we see the same type of process. And that is basically the testimony of the interaction of the defects with those dislocation lines. What we have to realize is that transmission electron microscopy pictures are 2D projections of a 3D configuration. So in the material itself, the zigzag aspect will translate most likely to a helicoidal configuration. And there has been some simulation studies that show that to climb a dislocation can modify its shape into a helix, and it will make it easier for it to climb. That process of climb is can be at the source of the enhancement of creep under irradiation. So I gave a little bit of example of how radiation damage can be studied through in situ irradiation in the TEM. I want to show another application. This is more fundamental study on how irradiation impacts the grain size of metals. And in such a study, we were looking at nanocrystalline metals, pure metals for that matter, that had a size, initial grain size of about 10 to 15 nanometer. As soon, and we're looking at how the grain size and the grain size distribution were affected by irradiation. What we observe is that regardless of the material, after irradiation, we see a gradual increase of the average grain size. And it doesn't matter the material, but also the type of ion, argon versus krypton, and the temperature. And we did such experiments even at 20 Kelvin, where the diffusion processes are extremely limited. So that, and we observe this type of grain growth under irradiation in zirconium, presented here in the case of zirconium. This eliminated the idea that the ion beam heat, the heat generated by higher ion beam, can be at the origin of this grain growth. Another aspect that also helped in the experiments was the geometry of the experiment. We were using samples upside down with the TEM grid on top of the sample. And because of this, the thickness of the grid and the fact that the ion beam were coming at a certain angle, about 16 degrees, we had systematically a region very close to the TEM grid that was shadowed by the grid and therefore was not hit by the beam. So for each experiment, without having to do any covering or any special trick, except for this one, looking at it upside down, we were able to have information on the region irradiated at the center and the non-irradiated region right nearby. And this is a typical picture that we could observe with a clear delineation, a clear delimitation between the irradiated area where you had evidence of grain growth and the non-irradiated area nearby where there was no grain growth. So this also was further proof that beam heating, ion beam heating, is not responsible for grain growth. This type of grain growth is due to the irradiation process itself. If it was due to beam heating, you would have thermal heat conduction because those films are metals, and you would not have a very sharp delimitation between non-irradiated and irradiated region. You would have grain growth all over the place. The curves where we could do the kinetics information that I was talking about earlier. Again, here, thanks to this process of capturing pictures as the process happens, we are able to follow with detail the average grain size as a function of those, and then we were able to fit it to this type of equation, where N and K are the fitting parameters. What we observed was that regardless of the material, the N exponent was close to 3, the value of 3. So that had to be something that the mechanism is responsible of grain growth under irradiation is responsible for. But what we also observe is that the K parameter, on the contrary, or in contrast, was dependent not only on the material, varied with the material, but also with the temperature, and therefore, and the irradiation conditions as well, whether we were using argon or krypton. So the idea, so in the end, the experimental observation allowed us to make those two major conclusions. And the whole goal of the study was to try to develop a model that will account for these kinetics. For sake of time, I'm not going to go over the derivation of it. It's actually in this paper here from 2008. And we basically came up, or based on the literature and previous work, etc., we have developed a model that accounted for the kinetics. The idea was that this thermal spike model for grain growth was based on the idea that ions, as they go through the material, they will create those point defect cascades here and there whenever you have a transfer of energy that is large enough. And only through additional experiments, we were able to show that only thermal spikes or defect cascades that were happening at the grain boundaries, only these ones were participating in the grain boundary motion. If you had thermal spikes inside the grain, those defects would recombine very quickly, and the surviving point interstitial vacancies would not necessarily help the process of grain growth, which is driven by the grain boundary migration. And based on this model, we developed an equation for grain growth, which was satisfying in the sense that we were able to capture the exponent of 3 that we saw in the experiment. And we developed an expression for K, which is very ugly, but also very satisfying, because that expression K was dependent on not only materials properties, such as the heat conductivity, the heat capacity, etc., but also on the irradiation conditions, the spike size, the point cascade size, the number of cascade per ion per unit depth, etc. If you're interested in this particular type of work, the whole derivation is in this article here. More recently, we have been applying this type of studies to studying defects in oxides. And this is part of an EFRC that I'm part of, where we're looking at how irradiation affects the corrosion processes. And for that matter, we corroded some samples of pure iron, and then processed some TEM lift out at the interface between the metal and the oxide, and those samples were irradiated. What we were able to see by doing systematic experiments at in the same condition but at different temperatures is an effect of temperature, but a difference between the metal region and the oxide region. And we started with 500 C, and the major difference was that defects would form and grow in the metal, while in the oxide nothing could be observed. At first, we started wondering whether it was something intrinsic to the material or not, to the oxide or not. We did the same experiment 300 C, and then same thing. So the oxide region were deprived of defects, while the metal showed formation and growth of defects. And we really started looking at the literature and started wondering what could be intrinsic to the magnetite that would impede the formation of defects. But what we observed during the experiments, especially in 300 C, by looking at all the different regions, is that there was an effect of thickness. And in fact, you can see only the thin region did not show defects. Wherever you have a thick region, you would see defects forming in the oxide. And you have a clear picture illustration here, where you have the same grains, the very large grains of oxides, but with 2 different thicknesses. And this is managed by the fibbing process, the sample prep process. We can control the thickness of the different regions in the sample by fibbing more or less those regions. And you can see here clearly that it's not in the thick part of the same grains, you have accumulation of damage and growth of loops, and not in the thin region. When we are at room temperature, it doesn't matter where you are and the thickness. At that point, you see the formation of defects. What is of interest also is the fact, again, that along the grain boundary, you have denuded zones, and that was also observed at room temperature, even at room temperature, and those denuded zones were pretty large, more than 60 nanometer on each side of the grain boundary, which means that in the end, the radiation-induced point effects and the small clusters are in fact mobile enough to favor the loss at sinks, including free surfaces or the grain boundaries, before they can clustering takes place and the loop formation takes place. That is at least to explain why we don't see defects at 500C and 300C. But that tells us about an enhanced mobility of defects in the oxide. First question that we have is, isn't it just radiation enhanced diffusion, which happens everywhere, but specifically it happens anytime that you have irradiation in your material, the point defects, the diffusivity are going to be affected and usually enhanced. But this picture is not that simple. It's actually complicated by the fact that when we compare the oxide and the pure metal, we don't see the same behavior, because radiation enhanced diffusion will happen also in the metal. In fact, the migration energies for the interstitials and the vacancies are very small. So if there was loss of defects to due to essentially or only to radiation enhanced diffusion, it should happen in the metal as well. So that's not the case. So in the literature, there's very few information on radiation damage in magnetite or chromium oxides or hematite, all those major scales that we build in a reactor. But there is some information on specific oxides, and we were able to see a couple models that show or discuss enhanced diffusion of defects in oxides. One of them is the ionization-induced diffusion, and that process relies on the fact that the migration energy of the defects in ceramics, such as oxides, may change with the charge state of that migrating defect. And usually it lowers the diffusion barrier, making it more mobile. That has been used to explain the amorphization resistance of some alloys, but it cannot be also the main it doesn't seem to be active in all oxides or to the same extent, because some other oxides amorphize extremely readily. For sake of time, I'm going to jump quickly. For another model that was found in the literature is that called the electron migration mechanism, where it has also to do with the charge state of defects in oxide. The idea is that if you're creating point defects in your oxide grain, let's say that the interstitials are more mobile, which usually they are, then the vacancies. If for some reason, for that reason, they start accumulating at the grain boundary before the vacancies make it there, you will have a space charge building up at that grain boundary. And that could further repel further interstitials from which are charged with the same sign, pushing them back into the grain. And there they can recombine with the vacancies which were too slow to make it to the grain boundary. And that could explain why you have lower density of defects, or that they're not forming large loops in those inside the grains. But this model has its own limitation. It only accounts for point defects in interstitials and vacancies with equal or opposite charges assigned to them. And whenever that's not the case for magnetite, for instance, or these oxides where you have interstitials, anion interstitials and cation interstitials that can be very fast also, and that can also go to the grain boundary. If that happens, this space charge will be damped, if not annulled. So in the end, we don't have a clear answer of why or how the defects are extremely mobile in the oxide, much more than in the metal. There's more experiments to be done and more simulations to be done, but magnetite is causing a lot of problems to modelers. All right, I would like to finish this by an example that is relevant to this consortium. In fact, it's a study that I started with my previous student who graduated now, but is now under continuation with Bruno, who's actually part of this consortium, where we look at the effect of irradiation in gallium oxide. And the reason why we're looking at gallium oxide is essentially for its properties and its potential as for use as a detection material. Gallium oxide has an ultra wide band gap, and that's actually why it makes it attractive as a semiconductor that could work at very high temperatures and very high powers, so in harsh environment. But there's not a lot of information on how it would behave under irradiation, in fact. The one thing that we know about gallium oxide is that it's polymorphic. It actually it can exist in 6 phases, but the most stable ones from a thermodynamic point of view is the beta one. So we have samples of gallium oxides that were grown by a collaborator at Bowling Green State University through different techniques. And 2 of them were actually even doped with different dopant, H and Fe, which has an effect on the gap width, basically. And in this experiment, we're looking at the effect of irradiation. So a few words about the most thermodynamically stable phase, which is beta. The beta phase. It's monoclinic. It has this structure here. For sake of time, I'm going to quickly jump into the result part. We irradiated these samples in the same facility that I mentioned earlier. We can observe the damage accumulation and compare. In this case, we were comparing the 4 types of gallium oxide that we had. But we were more interested in the phase stability of it. And that is an aspect also that you can get from electron microscopy by looking at the diffraction patterns. And if you see here, regardless of the gallium oxide, how it was grown or whether it's doped or not, when we look at the initial pattern we had for each of the cases, we had a beta phase, which is the thermodynamically most stable phase. But as soon as, as we started the irradiation, very quickly, less than a dPa, less in fact than 0.4 dPa, we start seeing extra spot and changes in the diffraction pattern, which, by the way, were indicative of phase transformation when the phase is identified, in fact, as kappa gallium oxide. And what we observe is that by irradiating furthermore, that phase was not changing. It's pretty stable. Thermodynamically, it's a metastable phase because the beta phase is the one that thermodynamic equilibrium predicts. There was further proof that of this beta to kappa transformation that can be assessed by looking at EELS spectra and looking especially at the ratio between the O1 and O2. O1 and O2 are the oxygen based on their position here. They are not equivalent. So when we are able to look at the ratio of those intensities, first we see that they clearly change after irradiation. And the decrease in this intensity ratio is related to this formation of the kappa phase. It can be attributed to either the increase of the O2, the oxygen that have the position, specific position in the monoclinic structure, or to the transfer of electrons from O2 to the 4p band into another band. So we observed this type of information consistently throughout, regardless of the sample and regardless of whether it's doped or not. Interestingly, the stability is not just under irradiation by further irradiating, but also over time. So I had my student look at the same samples 1 year after the experiments were done, and the diffraction pattern was extremely showed that the kappa phase is very stable even after a long time. So right now we have so what about the literature? This beta to kappa transition phase has been observed under ion irradiation in one particular study. It was done with nickel ions. But in that case, it was one dose, and the researchers basically attributed this phase transformation to the continuous accumulation of strain in the lattice due to the implanted ions, because it was bulk irradiations, not in situ. And they were mentioning that the implantation of these ions may cause excessive strain, and that would lead to this phase transformation. Our study, through in situ irradiation of the foil, we see the same phase transformation, but our study indicates that implantation of ions may not be a requirement to trigger this transition. Because in fact, if we look at stream calculations, we select our ion energies so that they are not implanted. We just want them to go through the sample, and we have extremely small retention, less than 2% throughout the sample. They induce the damage, but they go through, which means that this theory about implantation ions need not to be invoked to explain the phase transformation. And the other interesting part that we need to look at as well is the effect of the dopant. It doesn't seem to have any effect in terms of the phase transformation. This is an ongoing study, and that's what actually Bruno is working on now. We are looking also at the effect of temperature, because obviously those the application that I mentioned is for high temperatures, and we want to look at what happens at high temperatures. I would like to finish by with this slide to give some time for a couple of questions. I hope that I have illustrated the usefulness of in situ TEM for radiation studies. And thank you for your attention. If you have any questions now, let me know, or if you watch this video later, you can send me an email if you have any questions.
Thank you, Djamel. Thank you for finishing. We're leaving some minutes for questions. I just want to say thank you for the talk, and it's great to see all the work that you are doing at NC State. As being in the NSSC for a few years, first as a student, now as a faculty, I'm always amazed by the tremendous group of people and research the NSSC leaders have brought on board. The leaders like Dr. Vujicic and Dr. Goldblum. So it's amazing to hear that. And I want to open it so thank you for the presentations, and I want to open it for the participants if they have questions. I don't see now in the chat, but feel free to raise your hand or just unmute, or you can, like always, send them, I guess, as an email to Dr. Kaoumi. If there is before anyone else, I wanted to actually ask a question myself. It's like, as I've done nuclear reactor designs for a few years, I know how important materials are, probably the most limiting or the most important things to consider. So the question I have is, I've seen, you're doing all those experiments and gathering all those like important data and publishing all these papers. My question is, are you planning on it, like using those data for like, using maybe in the future some tools like or some groups at NC State of using like machine learning or AI to predict what you learn from those materials and those studies would which the consequences for other materials in the future, for future reactors, or what do you expect in long term?
You are very sharp in asking this question, I think, because this is really something that the community of the in situ irradiation is solicited for, because machine learning needs a lot of characterization, a lot of kinetics information, and in fact, there's now groups I know in Europe and as well as in the US, trying to gather all these movies, these videos that we are capturing for different materials to build a library that can be used later on for machine learning. Because this is really something that machine learning development needs.
Yes.
After NC State, we have not started such an effort. But I was solicited by the manager of the facility, asking if we could use all those material, the data, and there is an effort to try to get all the community to share some the data, the pictures, so that we can build or help develop machine learning tools.
Yeah, this is great to
the
hear.
field is going to. Absolutely.
Yeah, this is great. And I might contact you in the future because there is some work we are interested at UT on this regard. But I saw Bethany, you have a raised hands if you want to ask a question.
Hi, thank you. This is Bethany Goldblum from Berkeley. I just wanted to ask how, or what do you think are the most important investigations or avenues where this work will help to address nuclear security vulnerabilities?
Understanding or characterizing material that may have that can have a relationship with security issues or post explosive maybe material. Having a characterization of material, I think, is something that is needed. So developing the expertise for that, I think, is extremely important. Trying to understand how a material behaves. This particular either post event to try to understand what happened during that event or how the material has changed, but also in this particular case, the use of detection materials, the development of new detection materials that can withstand extremely harsh environment is something that depends on their radiation behavior. And a lot of the time when we have a novel material, and such as gallium oxide, novel in the sense that the application is novel, we don't know how it behaves. For instance, in this case, we don't know how it behaves under radiation. Is it the gap band is extremely large. It makes it ideal. But will it withstand a very harsh environment? Can we actually use it as a detection material? That, I think, is where radiation damage studies can be relevant. Don't know if I answered your question, Bethany. No.
Yes, thank you.
So I want to thank the speaker once more. Thank you, Djamel, for the overview of this tremendous work you're doing at NC State. And I want to encourage, if there is no question now, for people to reach out, and I'm sure there will be a lot of opportunities for work. And actually, I'm very interested about these efforts for machine learning. So we are looking at to do some things to gather all those data for doing special optimizations for certain materials. So
I would be glad to work with you, Sandra, if you in the future we can.
Perfect. Thank you again. And if there is no more question, we reached the top of the hour. So thank you everyone for joining the talk, and thank you again for presenting the work at this webinar, and Ava for putting all together like always and having patience when we have technical difficulties. So thank you so much.
Thank you, everyone.
Thank you.
Thank you. Bye.